Okay, so let's get started. I'll first introduce Dr. Karthik Desingh, who is an assistant professor at the University of Minnesota, where he leads the Robotics, Perception, and Manipulation Lab. And the lab is also affiliated at the Minnesota Robotics Institute. So I got to know Karthik a long time ago. We both graduated from University of Michigan, and we both did a postdoc at University of Washington with Data Fox. That's how we know each other. So we often talk about our research and career, right? So it's very exciting to have Karthik here today to give the guest lecture. And the topic is about object assembly, a spatial geometric reasoning pathway to physical intelligence. So yeah, welcome.
Yeah, thank you so much. Hey, everyone. Yeah, thanks for the kind introduction, Hugh. So yeah, I was just telling you that we just had a post CNN assignment in my class last week, which is one of the seminal works in the field of post estimation using deep learning that Yu Xiang had produced. So yeah, so great pleasure to be giving this guest lecture. So I'm giving this content for the first time, so feel free to stop me if things are not clear. And if you have any questions on the chat, maybe you can you look at the chat questions and ask me if there are any questions.
Yeah, sure. I'll be
Yeah.
monitoring the questions.
Okay, cool. So I wanted to talk about object assembly today and why it's important. And towards the end of the lecture, I hope to convince the students that object assembly is an important task, and it's actually a pathway to physical intelligence that we want robots to have. Okay, let's start with object assembly. And let's ask ourselves, why is object assembly such an important task to focus on? Object assembly is actually a subset of a lot of robot object interactions that we can think of, right? Like, so maybe we should be asking the question, why object-object interaction is such an important problem or a task to focus on in robotics. So let's look at this video. So this is the dream in the future, right? We want to have general purpose robot. So we will order a robot from Amazon. We just unbox it, and the robot works out of the box, right? No issues whatsoever, no hand tuning, and this is what we dream to have. Robot just cleans the environment, interacts with the objects seamlessly. Sometimes I'm not even looking at the object. And we would like to have such robots in the future. And I think that's what people have in mind when we say robots, right? And the important task is we want the robots to be useful to the humans, which means the robots have to perform tasks with the objects in our human environment. So let's ask the question again, why is object-object interaction such an important task to focus on in robotics? From the video that we saw, several tasks that was shown in the animated video basically has the robot interacting with objects almost all the time, right? And when I say object-object interaction, I'm talking about robot holding an object and then interacting with another object in the environment. This could be contact-free, it could be contact-rich. So when I say robot-object interaction, object-object interaction becomes an extension to that. So I think we have no doubt that object-object interaction is very important to look into, so we can have robots that can help humans. Now let's come back to the question, why is object assembly such an important task to focus on? The reason being, object assembly, although it is a subset of object-object interaction, it actually has a very good insight from cognitive neuroscience, developmental psychology, saying that humans tend to understand the physical world much more when they start actually interacting with objects in their environment. So an answer to this question could be that this is probably a pathway that would lead to robots' physical intelligence. And the reason for this is we are not stuck to these set of objects that we played during our childhood. We can actually perform a lot of complicated object-object interaction tasks. For instance, charging your phone, putting a battery into your lawnmower, opening and closing your water bottle, or even like inserting K-cups into your coffee machine, right? So we are talking about a physical intelligence, which is a form where the agent, this could be human or the robot, is able to interact with novel objects seamlessly. So I want to emphasize the word novel objects here because we don't want to stick to the objects that the robot had access to. We want it to be moving towards any object in the environment so it can understand the physics and geometry behind it and interact with the objects. Okay, so far, I think I have tried to convince you that playing with a lot of objects in the context of object assembly can help build physical intelligence that could lead to robots being able to use any novel objects in the environment and perform tasks. And these tasks need not be object assembly. They could be just object-object interaction tasks. So again, we posit that object assembly tasks can lead to this physical intelligence that we want for our robots. Okay, but we don't have robots that can actually do really good object assembly yet. So how do we enable robots to perform object assembly tasks? Object assembly is not new. Robots have been doing that for a while. So for instance, in industrial manufacturing, where the environment is kind of structured, robots have been able to do object assembly as long as they have been programmed to do it. Here is an example. This is from almost a decade ago. I want to say maybe 8 years ago, where the robots are basically assembling an IKEA chair. I want you to pay attention to the task a little bit more and understand, is this novel object assembly? What are they not telling you in this video? And also, look at the insertion task, especially when there is a spiral motion. So if the students are paying attention to this video, you should note that the bottom half or the bottom section of the chair has been stuck to the table. The objects are not moving, which means this could be a very well pre-programmed or well-initiated or well-structured problem in a way. But there is a camera on the right side or on the left side. So maybe it is doing a pose estimation on a known geometry of objects, right? So a set of objects or object parts whose 3D models are already known. The behaviors of the robot is probably already programmed. So maybe there is a collection of behaviors. And then it's all about estimating the pose of the objects followed by executing the sequence of actions. So they claim that this can be done in 8 minutes. And this was a big feat when it came out in 2018. And I totally remember when my entire lab went gaga when they saw this video of robot assembling the IKEA chair. But what we are talking here is about performing object assembly on novel objects. Okay, how do we humans do this? So there is an evidence from neuroscience and cognitive science that supports that humans employ spatio-geometrical features mediated by some neural pathways and cognitive processes to perform the assembly task. I'm not a neuroscience and I'm not a cognitive science expert here, but these insights are very useful to understand that spatial geometric features are being used for doing object assembly tasks. You might have heard mental rotation. So these are some of the concepts that stems from those ideas. But what I wanted to take away from here is that humans employ spatio-geometric features to perform assembly tasks. So with that, we can posit that the robots need such representations. When I say such representations, I'm talking about spatial-geometric features to learn null object assembly skills from some demonstrations. So let's say we try to come up with a task inspired by the Lego puzzles. We designed some object pairs with various peg and hole geometries. Peg and hole geometries are like commonly considered to be object assembly, the canonical task for object assembly. So let's stick to that. And these are some shapes that we 3D printed. As you can see, there's an arrow, there's a key, there's a U, and there is a pentagon. So just by showing these objects to you and describing, I'm able to describe the shapes. And I'm sure when you're looking at the screen, you are like, oh, so that has a key kind of shape, that has a U kind of shapes. So you have some sort of geometry that you're already forming, and you know how to manipulate these blocks to assemble them together. Now the assembly process would look like this, where in the space, if you have these object pairs, all you're trying to do is form some sort of mental rotation so that you can assemble them into one piece. So this is the problem scope that we're going to talk about. So there are a bunch of object pairs with peg and hole geometries, and we want robots to perform the assembly task. And we want to see if the robot can do this for null objects, just using these spatial geometric features that could stem from, let's say, a camera image or camera observations. So let's talk about the task a little bit more. So here is the robot performing this task. So it's a dual arm robot, and it has these objects in its gripper. So again, the task starts off like this. So there is no grasping involved. So we assume that the robot already grasped these objects. And let's say in this particular image, we have two objects, two blocks with extrusion and intrusion geometries that looks like a peg and a hole. The observations, especially for this real world robot experiment, comes from this top view camera. So this is the sensor observation that the robot sees. So the task starts off like this. So the robot has this two geometries and it shows to the camera, and then it figures out how to rotate or move its grippers to be able to perform this assembly task. So this is the example of how the task would look like if the robot performs this task. Okay, so let's set some objectives for this project. So the objectives are, first of all, because there is a dual arm robot, we want to learn dual arm manipulation policy that could perform this object assembly. We have two setups, one in the simulation, this is using PyBullet. The other one is in the real world, which you just saw in the previous slide. We would like to come up with a policy that works in both these environments. The second thing is what we actually are interested, which is the spatial geometric reasoning task. So we are trying to figure out if just by using visual information, if the model can perform this spatial geometric reasoning and do the object assembly. So I want to go through these shapes and the associated complexities. So on the top, what you see is order 1, which means there is only one solution, like one unique solution, right? So a U-shaped, you can only put it in a particular way. Order 2, which means you can have two solutions. So a minus sign or a hexagon or a diamond, you can put them in two different ways. The other one has 4 solutions or many solutions, which means if you have a, let's say, a cylindrical shape, you can put that in any way. As long as you can orient yourself to the cube, we consider that to be successful. Does it make sense? So far, the object pairs that we use have different complexities, and we don't want to give this information explicitly to the robot. It has to just figure that out from looking at the observations, the visual observations. The third objective here is that we want our manipulation policy to be robust to these grasp variations. The reason to have these grasp variations is because although we assume that the grasping is already done, we know that grasp variations could actually be a huge problem in doing object assembly. So we want to understand how much of impact does it have. And we have these 4 different variations. One is X translation, Z translation, Y translation, Y rotation, and then 4 different rotations on the Z axis. Yeah. So 3 objectives: learning dual arm manipulation policy, and then performing spatial geometric reasoning on a bunch of shapes, but also being robust to grasp variations. This is what we want to do.
Karthik, one clarification question.
Mm-hmm.
So in this case, the pair is already given to the robot, right? The robot doesn't need to select the correct pairs to do the assembly.
Exactly. So the pair is already given.
Okay. So then it's need to figure out how to put them together.
Yep. Yep.
Okay. Thanks.
Okay. So again, we hypothesize that the robots need geometric spatial features to learn to perform novel object assembly. So that's the premise that we are going with. So around this time, we also found that there is a lot of explosion going on in computer vision, which was giving a lot of pre-trained visual models that we could use. We don't actually have to train them again. We can just use them. And these are some of the three examples that we used in our project. One is CLIP, the other one is MAE, the third one is R3M. So I don't know how much of knowledge students have in this class on these models. So I'm going to give a brief overview of what these 3 are. So CLIP, this was by OpenAI in 2021. It's abbreviated for contrastive language image pre-training. The bigger idea here is that they came up with text encoder and image encoder. And they learned this using the contrastive learning mechanism, where if you look at the screen, so if you have a bunch of images, and if it goes through an image encoder, which gives you these latents, and similarly for each of the image, you have a paired caption. And if all of these captions go to a text encoder, you have these text embeddings. The idea is to maximize the similarity. So if you take a dot product of these 2 embeddings, you want to maximize the similarity and minimize the non-diagonal elements. Simple trick, and they have shown that this works extremely well. And especially this is one of the key principles behind DALL-E, which takes a text and produces an image, and many other techniques that came after this. So which means CLIP was able to understand some sort of semantic information about pictures from grounding that to language information. The other pre-trained model that was very popular was this masked autoencoder, shortly MAE. The idea is they wanted to beef up the encoder by giving a hard task during the training. So during the training, they will mask up some of the patches in the image, and they want the encoder to encode that information, and the decoder would decode the original image before masking. So as you can see, the encoder is actually bigger, which means they want encoder to perform all the task of reasoning among the patches. And so it actually focuses on the syntaxes within a particular image, whereas decoder is actually only used to perform the training objective. So this is the encoder that we are interested, and we are hoping that this could give us the spatial geometrical features that we care about. R3M is another pre-trained network. Instead of using the images from the internet. They use this Ego 4D dataset, which has the egocentric view of users performing tasks, which is kind of close to what robots would see if their sensors are moving or if they're static and the hands of the robots are moving. So they use time contrastive and language video alignment to be able to train this visual representation model. And they have shown that this works extremely well in some of these visual motor policy kind of benchmarks and data sets. Okay, so again, why do we care about these three? Because we are looking at some sort of existing models that we could just use, hoping that they would have this spatial geometrical features encoded, because these models that we see in the screen have been heavily used in the community of computer vision and also in robot learning. So the idea is we have some sort of vision encoder that uses any of these pre-trained models, which means given an image observation, we should be able to get good representation that has the features that we care about, and then learn a manipulation policy which could give robot actions. Now, this could be thought of as a supervised learning, where you have action for every image observation. So which is basically behavioral cloning, right? So behavioral cloning from demonstrations is what we will use to train this robot to perform this object assembly task, where we would evaluate the vision encoders and see which one works best for us. So here is the setup. This is the manipulation policy learning framework. So we have three views that we are using. So top-down view, left wrist view, right wrist view. So these are the visual information that we take from the robot, and they are resized and fed into these vision encoders. So we would use one of the vision encoders, right? And then we get features for each of these visual observations. And we append the robot's proprioception, the absolute gripper pose at that point, and then have a couple of fully connected layers to output the absolute gripper pose that would then be fed to the robot to perform the task. So this is basically looped so that the model outputs the next the position of the gripper that the robot actually has to move towards. So the reason we have 18 for the absolute gripper pose is because we have two grippers, so 9 values each. When we say 9 values, 3 values are for X, Y, Z, and 6 values are actually coming from the 2 columns of the rotation matrix. It turns out this is a much better representation for robot learning, and our paper has some ablation results on other representations as well. Anyways, so this is the manipulation policy framework. So we have visual observations coming in, and there is a vision encoder, gives you features, concatenate the features, followed by MLP to predict the next set of gripper poses. How does the demonstration data look like? Because I talked about behavioral cloning, right? So this is the demonstration data. So I'm showing you 5 examples. And if you pay attention to this particular column here, let me play the video again. You will see, sorry. So you will see that the robot has to rotate it completely before it aligns and performs the insertion. This is because of the ZR rotation that we talked about earlier, where the robot could have been grasping it completely on the 180 degrees for this particular task. So let me play this again. So you can see that the robot is completely rotating it to perform the. So again, this is the data that we provided. And the way we collect the data is using scripted demonstrations, where the scripted demonstrations are object-centric. So if the objects if we know the object locations and where they have to be aligned and where they have to be inserted, we could just use randomized grasp positions for the robot gripper and collect demonstrations. So that's how we collect demonstrations for learning this policy.
One question here.
Mm-hmm.
So sometimes the robot need to rotate the objects, but in some cases it doesn't need to, right? Then that means the robot has to learn from visual data which cases it should rotate, correct?
Right. Yeah, exactly.
And these are more from the whisk camera, right? Because that's more visible for the objects.
Yep.
Okay.
So
okay.
we have an ablation theory that says that having wrist views helps us much more when it comes to rotation. And if you do not use wrist views, then you don't actually understand the rotation better.
Also in the drill robot, you also have the whisk camera.
We did not for this particular paper. For the one that we talk about later, we have the whisk cameras for the real robot.
I see. Thanks.
Yeah. So yeah, so like I said before, this is the simplest recipe, right? You have observations. We are encoding the vision using the pre-trained models, or you can also train from scratch, and then followed by policy network, which is basically an MLP with 2 layers. So we evaluated these pre-trained models that I spoke about earlier. CLIP. There are 2 variations of it. One is on VIT, which is transformer model, and then ResNet 50. MAE, masked autoencoder, the VIT version. R3M, ResNet. And then we also used ImageNet pre-trained VIT, ImageNet pre-trained ResNet. And lastly, we also trained from scratch. So we did not use any pre-trained network. We trained from scratch. So these are 2 versions. One is pre-trained ResNet 50 and pre-trained ResNet 18. Surprisingly, we found that the non-pre-trained ResNet 18 outperformed all of these other models. We think that is because the pre-trained networks has not seen similar visual information in their pre-training. So maybe there is a domain distribution shift that we could not think of before. But there is also some interesting insights that we gathered in terms of the rotations that were induced by the grasp variations. So I'll talk about that in a bit. I want to show quickly the results, the visual results from our non-pre-trained ResNet 18 model. So let me play this again. So here are some examples where you're able to successfully perform the insertion. Again, the robot does not know which geometry it's looking at. All it is getting is these visual information, and it has to figure it out from there. Okay, let's dive into the results a little bit to understand what happened and where do the pre-trained models do not work really well. So I want to highlight the different task variations or grasp variations that we have. One is the x-axis translation, we call it XT. Z-axis translation, we call it ZT. Y-axis rotation, we call it YR. And Z-axis rotation, we call it ZR. So with that in mind, let's look at the results. So with simple translation and rotation, we can see that pretty much all the models actually perform really well for the translation. They have some gap in the Y rotation, but they actually struggle quite a bit with the Z rotation that we see here. And this was actually trained with 100 demonstrations. And we can see that these are really good, whereas the Z rotation is causing the error. So again, we are highlighting the fact that the non-pre-trained ResNets actually perform really well in these tasks. Now, how about some combination of these grasp variations? So here we look at combination of grasp variations. So for instance, you have XTZR, which means it's a combination of this and this. ZTZR, so you have this one and this one as a combination and so forth. The last one is the combination of everything. And we can see that when you have combination of translation and rotation, which is often what you will see if you let the robot grasp any object, we can see that even non-pre-trained ResNet model performs really bad with this combination. And also, I don't know if you noticed, we went to 1,000 demonstrations and not 100 demonstrations. We had to move to 1,000 demonstrations to achieve this accuracy on the combinatorial grasp variations. So if you pay attention, the ResNet clip ResNet 50 tends to be somewhat closer to what we see in the ResNet 50. That was a surprising result. We don't actually have a very good insight on why that happened, but this is something that we kept seeing across different experiments. Okay, and we also wanted to see like what sort of geometric reasoning is harder when we have this combination of task variations. So when we started going towards the peg and the hole that had a unique solution, which means it had no symmetry, in that case, we saw that there was a huge drop in performance. So what I'm trying to say is maybe these models are not performing the spatial geometric reasoning that we want to. But however, this gives us a nice idea to think about what sort of variations should we actually focus on to understand and do the object assembly really well. Here is the attention map on these models. So you can understand what these models are actually focusing on when you give a visual observation. So the first two columns are basically the non-pre-trained ResNet 18. You can see that their attention maps are somewhat similar. And clip ResNet 50 that we saw, which had closer performance, also has similar attention maps, where all of these three models are paying attention to the gripper, the finger, and also the peg and a hole in certain cases, the corners and edges. Whereas ImageNet ResNet 50, the ImageNet VIT, the clip VIT, it was kind of all over the place. So this is another interpretation to tell us that the non-pre-trained ResNet 18 could be a new benchmark that we want our pre-trained models to get closer to. Okay, so how did we do this in the real world? Here is our real world setup for data collection and evaluation. The first part is for each episode, the objects are picked up with a random grasp variation from this particular pedestal. So they are basically placed in this location, but every time for every episode, you actually have a randomization on the grasp variation. And once it is picked up, it is being shown to the top view camera. Again, note that the real world setup does not have wrist views. And it performs the scripted expert trajectories. And we collect this demonstration with the robot trajectory as well. After this episode, robot places the object back onto the pedestal, and then we can start again with a different grasp variation.
Is this for collecting demonstration to train the policy?
Yeah.
So you also train the policy with real world data.
Right. So there is no sim to real going on. So we have to collect the data again on the real world.
Okay, thanks.
So this is the real world demonstration data that we have. So be it scripted in such a way that we have three phases. So one is moving to an alignment phase and then performing the alignment and then doing the insertion. So there are three phases to to do this task. Here are some rollouts on the real world robot. So let me play this again. And we are only showing it for one particular object here. You can see that some of these are almost nearly like assembled. And we found that most of the cases, it's almost this close orientation where you actually have a lot of failures, which tells us that maybe we should start using force and torque sensing to complete the insertion. So maybe the visual information can guide you until that point, and once you make a contact, you probably need to think about using force and torque sensing to complete the task. So here are some more examples talking about the same thing. So here with the Z rotation, you can see the robot was not able to figure out the orientation, so it failed there. Couple of failure cases on the x-axis translation and the y-axis rotation in this case. But in almost all these cases, except for the first one, we can see that the failure is almost nearly in the location where we want these objects to be. Okay, so there might be several questions in people's mind so far. So what if we fine tune the pre-trained models? What if we give more data? How much impact does proprioception have? Does object texture help in performance? Because we don't actually have textured models, right? How does the model perform when the geometries are perturbed from the training distribution? Meaning, if they are not necessarily in the center, let's say the U shape was rotated a little bit, how does these rotations of the peg shape can impact in the performance? So we did experiments on a number of things, and if people are interested, please look into our work much more. So you can understand how these things impact the performance. Okay, so I want to go back to the question that we asked earlier. So humans have these spatial geometric features that they use for object assembly, and we posited that like robots need such representations to learn novel object assembly skills. And where do we stand at this point? So we can do the policy learning with no explicit object geometric knowledge. We thought visual information is good enough. And we thought the pre-training visual representations are good enough to give these features. What we found out was that this is not necessarily true because of the distribution shift. And the visual information might not be good enough, especially in the real world experiments. We found that the nearly miss was basically because we did not have any force and torque sensing. For no explicit 3D models or object knowledge, I think that was a fair assumption, and I think it worked out for us in terms of doing the task. But for the other two, I think we need to work a little bit more. So that's where the next work comes in. So this is the most recent work that we archived. It's called AugInsert. This is learning robust visual force policies via data augmentation. So let me set up the problem in this particular scenario. So again, it's a peg in the hole, dual arm manipulation. So there's a peg on the whole object. But now we're going to use the force and torque sensing. We are not going to use the top-down view because we thought that was redundant. So we're going to just use the force and torque view on the left wrist view and the right wrist view. The thing to note here is that the task starts exactly like this. So which means we are not bringing the object all the way to make the contact. The task here starts with the contact. So it's only contact-rich manipulation. Okay, so now what are we interested in this work? In this work, if there is no variation during the demonstration collection, we want the system to be performing really well to observation level task variations. So let me show you what we mean by the observation level task variations. One task variation could be that we will change the peg and the hole shape, the peg and the hole body shape. So in combination, we can have about 54 total object shapes for this particular experiment. So when I say peg in the hole, I'm talking about the exact peg in the hole shapes, and the body is basically the body that the robot, the objects have. The other task variation is again the grasp variations that we saw in the first work. So we want to still be able to do this under these grasp variations, especially the rotations we are talking about like minus 10 to 10 degrees, and the translation we are talking about 2 centimeters. And for ZR rotation, we are talking about the 90-degree offsets. We also want to be able to perform if the scene appearance or the lighting condition changes. The other task variation we want the system to perform well is the camera perturbations. So for instance, if we kick the camera a little bit, we'll have a small perturbation that we want to be able to handle. We also want to handle noisiness in the sensor, especially in the task in the force and torque sensing. So these are all the task variations we want the system to perform, but the human provided demonstrations are only the canonical demonstrations. Okay, so the data collection looks like this. So we have this in Mujoko, where teleoperation is done to provide the demonstrations in the canonical variations. That's what we refer to as without any variations in place. So this gives us human demos, and then we perform data augmentation. Basically, this is an online data augmentation where we replay the trajectory on the environments and we apply these task variations. So this is actually a quite simple trick, and with this we can actually expand the number of demonstrations, at the same time handle all these task variations that we want to handle. Okay, so this is model architecture because we are not doing the pre-training followed by policy learning that we talked about earlier, because that simple recipe did not work that well. So here we look at the left vis view, right vis view, force torque sensor, proprioception. We have this the network that was developed using perceiver IO architecture, where you are tokenizing all the sensor data and together use cross attention and self attention to come up with tokens which are multimodal, and then use MLP along with the proprioception to get a really good feature that then gives us the delta X, delta Z, and delta Y. So note that there is no rotation. It's only translation at this point, because we assume that the previous work has already brought these two blocks in a very close proximity, and delta X, delta Y, delta Z should be good enough. And any variations that we expect could be induced in the grasp variations that we talked about as part of the evaluation. Okay, so let's look at the results in this particular work.
Can you talk a little bit more on the force torque signal? Why it's like 32 by 12?
Yeah, good question. So the left vis view, right vis view, they are 3 cross 80, 84 cross 84 because they are RGB images. The force torque signal, it has a history of 32 frames. So we always use 32 frames followed by the 12 values. 12 values comes from 6 values from each end effector, where 6 values are 3 values for the force and 3 values for the torque.
That's on the waist of the arm, right?
Yes.
Okay. Thanks.
So we are using UR5E, and it only has force and torque on the wrists.
Mhm.
Yeah.
Thanks.
And one cross protein from the proprioception is the quaternions that you have from both the end effectors. XYZ followed by 4 values that talks about the rotation.
Mhm.
Okay. Yeah, I would highly recommend people to look into the perceiver IO architecture, which is what we are using here as a transformer encoder. Okay. I'm going to quickly show some highlights of the results and our findings here. So let's say you train the policy on no variations. So again, this is no variations, just using human demonstrations and testing on these canonical environments without any variations of any sort. We can see that we can perform this task with almost 100% accuracy without any variations that we talked about. Now, if you start perturbing the grasp pose, the success rate drops like drastically. This goes almost to 0. So again, the model was trained on the canonical views, and we tested on the scenarios where there is a small perturbations to the grasp poses. Now, if you add more data, more variations to your training, so in this case, we are adding visual variations and sensor noise to the training. Rollouts on the canonical environments remained really good. They are like almost close to 100%. The grasp pose environment, where we added perturbation to the grasp pose, slightly improved, but not quite a lot. Only when we added object shape and grasp variations, we started seeing some improvement in the perturbations that are induced by grasp variations. So we went up by 60%, which is what you're seeing at the bottom. Top again, we're still maintaining the same accuracy that we had on the canonical environment. So adding variations, we are not losing too much on the canonical, but we are seeing some improvement in the grasp pose variation, not to the level of 100%, but we are at a point where we can do this with a 60% accuracy. So this tells us that the grasp variations are actually really hard to be robust on, especially in the context of assembly tasks. We did some real world experiment as well. So here is a real world data collection. Again, we are doing delta X, delta Y, delta Z. So we used a joystick to be able to do this. This is a data collection. And then here are some data collections with the observations from the wrist cameras and also the force and torque sensing from both the wrists. So what we see in the real world evaluation is that we are getting a really good success rate on the canonical environments, meaning tested and trained on similar scenarios. So we get about 90% success rate in that scenario. But when we add body shape variations on the canonical model that we trained, we can see about some drop in the performance up to 80%. But grasp variations is a hard problem that we found, where the success drops down to almost 15%. So the key insight here, again from the real world experiment, is that data augmentation may be necessary to improve the robustness. So just like what we saw in the simulation, if we add more grasp variations and more object shapes, that could improve the performance. So that's the observation that we have from this work. Okay, so I want to go back to this slide, where there is an evidence that humans employ spatial geometrical features to perform object assembly task. We did attempt to understand the visual features, if they have this particular spatial geometrical reasoning ability, And what we found was not necessarily the case. And our insights tell us that we need force and torque sensing. Maybe that is required in the spatial geometric feature learning. And maybe not the existing pre-trained networks are not necessarily good because they don't have this notion of contact-rich manipulation, which is key in object assembly task. So some key takeaways from these two works is that task variations are really hard to be robust to in object assembly learning. Visual pre-training models, which are learned on internet data, is not necessarily best for object assembly, probably because they do not have this spatial geometrical features that we hoped for. Force torque data or some sort of tactile information is vital, especially during the contact-rich phase of object assembly. And we hope that we could come up with a spatial geometric feature learning that also incorporates the tactile information. Lastly, data augmentation tricks actually can help you accommodate observation level variations in object assembly task. This has been shown in other works as well, but we wanted to see how much it can have an impact in object assembly task, and we see that this can actually be a really good trick to have. Okay, I also wanted to point to some related works in this space because we are not the only people who are doing object assembly. So this was a paper that came up in 2021 from MIT. It's called KPAM 2.0. There's another work, RB2. This is for shape sorting. So this is the question that you was asking, like, are we figuring out where if they are compatible or not? So this is probably where you need to figure out where the particular hole is that is relevant to the peg that you're holding. And MimicGen has a few tasks that has multiple part assembly in them, so that might be interesting to people. There are also some works that does the visuo-tactile. So this is a work that came in 2019 that uses vision and touch and also self-supervised learning to be able to do this. And here is another work, which is actually a series of work. This is called Insertion Net. And if people are interested in looking at how you could use just the visual sensors to be able to do that, so they have some work in that. Okay, so that's all I had. We also have other works in the lab. I'm not going to go into the detail of that. I'm just going to play a couple of videos. So one is grasping for manipulation of larger objects. So this is the Spot robot grasping larger objects like chairs. So we have a supercube grasp method, which uses super quadrics, which are primitive shapes. This has no learning. This work has no learning in it. It's purely geometrical. And we find that this can give you better grasps than the state-of-the-art methods. And the other work is to be able to use language to do demonstration data collection. So this is focusing more towards the end user. So can end users talk to the robot and give demonstrations? And we show that you can actually hierarchically learn from actions to tasks to skills, and there is a benefit for doing that. So if you're interested, please look into this work. With that, I want to thank my lab. These are all the folks who actually do the work. I'm just presenting here. So thanks to all of them. And yeah, thanks for everyone for paying attention. I'm happy to take questions.
Yeah, thanks, Karthik, for the wonderful talk. So basically, robot manipulation assembly, right? It's a very challenging task. I think Karthik is trying to use this as a case study to learn what is the visual representation, what is the like a strategy to solve this problem, like data augmentation or tactile feedback and so on, right? So it's a very great talk. Yeah, let's start with some questions from the students. So, Sarab, you can unmute and ask the question.
Sure. Yeah, so Professor, like great, quite inspiring work and great presentation. So my question was, is there a specific reason that why you focused on dual arm setup? Because for like in real world, we have tasks like inserting a charger in the socket, which can be done with a single arm, right? So is there a specific reason why you use dual arm setup?
Right. So great question. I think for this particular set of works, we just happened to have dual arm, and then we started using that. But the bigger reason for using dual arm manipulation comes more like from like all the objects in our environment are designed for humans, right? So we design these objects, and there is an implicit understanding that humans will use them, which means either you can hold them with one hand or you can hold them with two hands. So the dual arm manipulation basically was trying to say that the future human assistants should be having two arms, because if you want the robots to work with the objects in our environment, which are specifically designed for dual arm agents, which are humans, maybe we should just start using dual arms. And in our case, it actually was beneficial because with two arms, we could start looking at objects with parts. So they're not necessarily peg in the hole. You can have like a cap and a bottle. So it still becomes an assembly task. So it gives us some ideas to think about how to extend these assembly tasks to, let's say, object-object interaction with the dual arm setup.
Okay. And I assume that this work can also be extrapolated to single arm uh, setup, because basically you keep the other arm fixed.
Yeah,
And
yeah, definitely.
Okay.
Yes.
Okay, thank you.
Thanks. Next, Yosh.
Yeah. So, Professor, why do you think the grasp variations are failing? Is the force toward reading different when the grasp is different?
Great question. So I think grasp variations can be hard because it gives you like the search space for doing the policy is quite large when you start looking at all sort of variations that you have with grasps. The idea is if the neural networks can come up with an abstract representation or a latent representation that could be useful to kind of abstract away the grasp variations and still be able to learn the policy. But we just saw it was not able to do that because of these rotations. So one thing that I was trying to allude to with evidences from neuroscience and cognitive science is the fact that we have this really good mental rotation. So even if I just show you a shape, there is a good reasoning that you have that, okay, this shape is here in the space. And if you make this particular motion, this actually, you can even predict what will happen with a specific perturbation in terms of the motion of the object. So my understanding that we still do not have such good representations, especially that stems from just observation data. So that's why we are still failing on that.
Okay, thank you.
Yeah, Desingh, you can go ahead.
Yeah. Hi, Professor. Thank you for the informative session. I hope you remember me. We met during last quarter. Yeah, actually, I have. Actually, I have like two questions. So first one is like more of an abstract question. So in the first work that you presented, like a lot of pre-trained models were used with like CNN variants and transformer variants. And also in the second work, you use the Persever IO architecture, right? So recently there have been state space models like Mamba VIT and all those things. So do you plan to use them somewhere down the line, or like do you have any thoughts on using them for robotic applications?
Sorry, which models? I think you broke.
State space models, Mamba VIT and all those things.
Yeah, so I guess So to just go back, I think when we did the first work, we actually wanted to have a simple recipe, like just like plug and play with vision encoders,
Mhm.
so we can actually learn the policy. And we were like, if that works, great, problem solved, right?
Right.
But because of the grasp variations, we were like, okay, this is still a really hard problem. And
Mhm.
mostly when we started using the real world experiments, we understood that the force and torque sensing has to be used. So in
Right.
order to incorporate force and torque sensing, at the same time as we understood that the visual representations are not that good enough, beyond a point, we just like focused on a particular transformer encoder, which is the perceiver IO based encoder. So
Right.
I think we are open to like trying different mechanisms as long as they can encode multisensory information.
Right. Thank you. The second one is like, I see like you have used a lot of demonstrations to train the model.
Right.
So do you plan to do some kind of few shot demonstration learning down the line?
Yeah, so that is something we are actively looking into. So there are a couple of works which are not matured enough, but we are looking into zero shot. That's one thing of interest. We are also looking into equivariance, if that could be helpful. Equivariant networks can actually be very sample efficient, meaning you don't need to show a lot of examples to talk about rotations, as long as the network can actually capture the rotation like explicitly. So yeah, so we are looking into that.
Yeah, thank you.
Yeah, thanks.
Any other questions from the student? Actually, I have a related question to the few shot. On the other end, right, people are looking at scaling laws in getting demonstrations to train the policy. So what if you collect much more number of demonstrations? Will that solve the grasp variation problem?
I think we also have to scale the objects as well, right? So maybe it could be a good experiment to try that, but I'm wondering like how much data efficient we should start looking at right now, so that we can still scale on like the variations of the shapes. So there is a two problems, right? One is scaling on demonstrations, the other one is scaling on objects.
Right.
I think we should focus on scaling on the objects. So I feel like scaling on demonstrations, it has to be very efficient. So if we can scale really well on the objects by having minimal amount of demonstrations, I think that might be a good way to go.
Yeah, thanks. And also, have you tried to connect the two work? As you said, the first work is trying to move the two objects into close proximity, right? And then the
Right.
force policy gonna assemble them.
Right. So yeah, so the reason we actually did this work was let me show you the. So the first author in the second work is actually the second author, or maybe the third author in the first work. So he was the one who was doing the real world experiments, and he was really frustrated when it was like really close, and he had to count that as a failure. So then he was like, okay, I'm going to use the force and torque sensing to solve the problem. But I think his work can be easily extended to do the all the way, like looking at the shapes and coming together. All we need to do is like use another modality, like sensing modality of top view, so you can actually look at the shapes really well, or have some positions where the wrist camera can capture the geometries beforehand. So one of my students is trying to integrate the system together. We'll see how much they're able to do.
Yeah, that's very interesting. As I have talked to you, right? We also add a force torque sensor to the batch robots. And I saw you already using the force torque sensing here. So that's very interesting.
Yeah.
Okay. Any other questions from students? If not, let's thanks Karthik for the wonderful talk. Thank you so much.
Thank you, everyone. Thank you for having me. Yeah, thank you, everyone. Happy Thanksgiving and happy holidays.